Okay, Schumann Resonances. We live in a special place. We live in a gaseous medium trapped between a conductive Earth and a conductive ionosphere. And that geometry sets up what we call the global electrical circuit. And there are two global circuits. There's the DC global circuit, which is very simple in concept. It's a giant capacitor, basically. And it's maintained by global electrified weather. And there's about a 250,000 volt potential difference between the conductive Earth and the ionosphere. Very simple concept, but very hard to measure that and monitor it continuously. Then you have a much more complicated phenomenon. We call it the AC global circuit, which is Schumann Resonances. And this is it really is a more complicated phenomenon, wave phenomenon. It involves standing waves in the Earth ionosphere cavity. Speed of light, the time it takes light to go around the world is 1/8 of a second, and so the corresponding frequency is 8 cycles per second. That's the fundamental mode of Schumann resonance. And it provides a natural framework for going after global lightning activity. Now, we know a lot about global lightning activity from satellite observations, which see lightning in the optical. We know that there are three major chimneys, what we call chimneys of lightning activity: the Americas, Africa, and the maritime continent. There's very little lightning over the ocean. There's an order of magnitude difference between the lightning over continents and over the oceans, and that has to do with temperature. It's hot, it gets hotter over the continents. But an order of magnitude difference in lightning activity. But the problem with this data is this is based on thousands of satellite orbits. So it's a climatology, it's an integration over many years. What we want is to have a continuous monitor of global lightning activity every 10 minutes for the whole world. And that can be provided by Schumann resonances. Now, Ted was a pioneer in this area, but there is a longer history. I'm not going to go into all the details here. Schumann, a German, made theoretical predictions. The US Navy knew about it. They knew about skin depths, and they knew that low frequencies would penetrate deeply into the ocean, and they wanted to communicate with submarines, and that led to a lot of support for work in this area. The classical paper on observations was by Balzer and Wagner in 1960, a Nature paper, and Charlie Wagner is here today. He was an MIT undergraduate. And then Ted, I'll show you some data that Ted worked on in 1960, showing the 8 Hertz fundamental mode and telluric data. But the best paper in this field is Madden and Thompson, 1965. And Bill Thompson is here, and Bill Thompson explained to me that he was the bridge between Ted on campus and Balzer and Wagner at Lincoln Laboratory. And Ted was doing modeling to explain Balzer and Wagner's measurements. The Balzer and Wagner measurements were made on a tower up the coast at Ipswich. They had beautiful, you could see the 8 Hertz spectrum very, very nicely. And then there's another important player here, who's also here, Phil Nelson, who was the first one to suggest using Schumann resonance in an inversion mode to get the global lightning activity. And there's another story associated with that. Phil Nelson was involved with measurements near Millstone Hill. Those measurements were made in a radome, and that radome is the same one that's on the roof of the Green Building. And you had to crawl into the measurement cavity through a porthole, but they had a capacitively loaded antenna within that radome at Millstone, and made measurements in the 1960s. The important work that enables one to do inversions and get the global lightning activity by inverting the background data is the famous Gray Peril. This is this document. Many of you have talked about it already. It's a very thin document. It turns out that Halima Madden typed this document years ago, and Ted asked her to single space it because he thought it was looking too long. You see how thin it is? So supposedly you'll be able to solve any inverse problem in the world with the material in this document, but the details are lacking, and so the idea was you use it at your peril. And that was Jerry Latorica's reason for naming it. And then there's other work in between, but basically that Madden 1972 provided a means for doing the inversion, and I'll say a few words about our progress on that problem later in the talk. Next slide is for me. Now, we went looking for smart rocks about 5 or 6 days ago at the Maddens, going through all of Ted's papers. We had some success and some lack of success, but we did find some interesting course notes from 1962, 12.88, Special Topics in Wave Propagation by T. Madden and W. Thompson, starting with fundamental Maxwell's equations for the Earth ionosphere EM resonance problem. This is when Ted was beginning to interact with Balser and Wagner and with his student Bill Thompson to learn about this phenomenon. But we also found this. Ted's first detection of Schumann resonances was in the telluric data. He put electrodes in the Earth, connecting two electrodes, measured the voltage difference between them, digitized the data. He didn't have Adolfo to do hand digitization in those days, so he did it himself, and he did his usual neat hand plot of the data, and did a power spectrum analysis, and lo and behold, 7.8 hertz, the fundamental frequency of Schumann resonance. That was in December of 1961. But the very best paper in this field, even till today, and I would say probably one of Ted's very best papers, is Madden and Thompson, 1965, in the Reviews of Geophysics. And it's typical Ted Madden, bringing observations together with theory in a very skillful way. Very nice piece of work. And using models that to this day, the models that are used today are not even as good as what Ted was doing in 1965. This is the transmission line, but wrapped around the whole world. So it's a transmission line surface, and the beauty here was he was solving a complicated three-dimensional problem with a two-dimensional model, which is a great simplification. This is the last note on science that I ever received from Ted, and I remember it was given to me on a piece of paper in this room sometime in the 1990s. As usual, very terse, but full of information. And basically, the night effects must include a lot of energy escaping, which was to say that with the model, with the Madden and Thompson model, with a nighttime ionosphere, John Claerbout mentioned the difference between daytime and night-side ionospheres, electromagnetic energy escaped the waveguide and went into space. In the last few years, there have been satellite observations, NASA, showing that, sure indeed, you do see Schumann resonances in space, but only on the night side. And the person who worked on that wasn't even aware, because so much time has gone by since Madden and Thompson, was not even aware that Ted predicted this, 3 or 4 decades earlier. Now they know. The other important step was Phil Nelson. This is his thesis. 1967, again, he worked with a single vertical electrode and a radome at Millstone Hill near the so-called farmhouse. And the first suggestion that you might be able to use is a network of stations worldwide to invert the data, invert the background observations, and get the global lightning activity. And here was a figure from his thesis showing the 3 chimneys that I mentioned before, Americas, Africa, and Southeast Asia, 15 yellow receiving stations just in hypothetical locations, and then showing that this was viable and with a summary statement, since a network of worldwide receiving stations will be able to furnish a good deal of subsidiary information about thunderstorm location, the source problem appears quite tractable when treated in this manner. So we started measurements, not at Millstone Hill. We had contact with a guy named Charles Polk, who was also in touch with Ted Madden and Balser and Wagner. And he had a site in West Greenwich, Rhode Island, and he said, if you're interested in this phenomenon, you can come here and make measurements. We're pretty much through with that research work. And so we went to Rhode Island, and we've been running in Rhode Island ever since. We've been running since the early 90s, and we built a very stout antenna. We didn't have a radome to protect us there, and we built an antenna out of big insulators that we got from Boston Edison. It's about 7 meters high, and with that we can see lightning worldwide. And we got interested in first the point source problem because of a discovery that my student made, Dennis Vocipio. He used to go to the Schumann Resonance site in Rhode Island, and he'd get on the telephone with Walt Lyons, who was operating a video camera in Colorado, and every time Walt Lyons shouted, "I've got a sprite," with these big luminous shapes in the mesosphere, Dennis would see a big Schumann resonant transient come across Rhode Island. And so that linked two phenomena, namely the giant lightnings, we call them mesoscale lightnings, that single-handedly ring the Earth's ionospheric cavity to levels above all the other lightning combined. And at the same time, there was a sprite at 80 or 90 kilometers, a luminous jellyfish-like shape in the mesosphere. And so that got to get us very skillful in locating lightning worldwide from just the single station in Rhode Island. And you can see, again, the three major chimney regions, the Americas, Africa, and the maritime continent. This is integrated over many months, accumulating many events. But it doesn't get the background data. The background data is the low-level ripples of resonance that are generated by ordinary lightning activity and ordinary thunderstorms, not these exceptional bell-ringing lightnings that occur in mesoscale convective systems. But I can remember when Ted talked about this with the apparatus in Westford, that he would see lightnings go around the world, energy packets going around the world on a scope, just connecting a scope to the electrode. So the background inversion is much more difficult. It's like, you can locate me as a point source as the speaker. I dominate over all the little whisperings in the audience, and I'm easy to find. But if you're trying to locate lightning in South America and Africa and the maritime continent simultaneously, it's the problem of detecting locations when you have many whispers in the audience going on. And it's a much more difficult problem. But fortunately, unlike the time of Phil Thompson, when there were probably 2 stations in the world operating, one in Rhode Island and one in Massachusetts, and maybe the Germans had something going, now there are about 15 stations, about as many stations as what Phil Nelson needed in the simulations to do the background inversion. And so we collaborate, even though it's not networked, we have collaborations with all of these sites. I visited Tahiti last November. It's a beautiful station with beautiful data because Tahiti stands back from all the lightning activity in the 3 major regions of interest. And you get very, very clean data, and you can see every day, you see the 3 chimneys turning on and turning off as the sun crosses them and warms the surface, destabilizes the atmosphere. So Phil Nelson's recommendation was we take the fundamental mode. This is the fundamental mode at 8 hertz. This is the Schumann spectrum. 8 hertz, 14 hertz, 20 hertz, 26 hertz. You can see modes all the way to the power line frequency of 60 hertz. And we make use of all of the information, not just the center frequency of the fundamental mode. That was the purpose of the mode tracker at Millstone. So we get, from any single measurement, we have 20 or 30 observables when we do Lorentzian fits to the spectrum and pull out the unknowns. And then just an example of one so successful inversion. We're still working on this and have trouble with the problem of multiple minima. Ted was well aware of that. It's a very common problem in inversion theories in general. But we can now get, on a single day, we can determine the source strengths in all 3 chimneys on a continuous basis and see the charge centers moving with time and see the migration of the system. We don't do very well in the Americas, and we think one of the reasons is that the forward model is flawed to the extent that we have activity in the vicinity of Tahiti in the Central Pacific, and that's confusing the picture a bit. So we're still working on this problem. It's not an easy one, but we're making progress. So that's Schumann Resonances. Again, I got a Smart Rocks t-shirt, and I want to say something about Smart Rocks. Thanks to Halima, we found the Smart Rocks. Okay, these are the 2 Smart Rocks. Ted had few vices. One of his vices was Halima. Another vice he had was in Earth Resources Laboratory, a big machine vice, a milling machine vice, yay big. And we did 2 experiments with that machine vice. The first was we made random networks in plexiglass. We used a random number generator to select crack locations on a hexagonal lattice and then we cut slots to make the cracks, and then we stressed the plastic in the vise. And cracks developed. And when a crack developed, it always took a lot more stress to make the next crack. And so Ted's comment was, these rocks, these simulations of rocks are really smart because they protect themselves. They develop cracks in such a way that they avoid further failure. And this will go on and on and on. The cracks would remain random. Dave Lochner talked about his results where he has a very homogeneous distribution of cracking until the very late stage. And then things get organized and you get this through-going crack through the whole system and the system fails. But the rock holds off for the longest time in getting to that stage. It stays homogeneous. And that was why rocks were smart. And then we got the idea of, coming back to the real smart rocks, this is a plastic bag, double plastic bag. There were 2 cylinders of, guess what, westerly granite, our favorite rock, right? For years. I got them from Mike Batzel. And one of the samples was in the vise, stressed continuously. We had a torque wrench to control the stress. And the other rock was, in the same fluid, 10 to the minus 3 NaCl, but outside the vise. So we had a control. And unfortunately, we cannot find the data plot. But Ted, for years, this experiment went on for the better part of a decade, I think. It started in the late 80s, I think. And so he plotted, in his typical style, hand plotted the points on graph paper, and he had them on the wall for a while. And I remember he would always call me over to see the plots, even after he couldn't talk clearly. And he was following that very carefully. And I remember the result. The result was that the unstressed rock was, as you expect, flat. With its connectivity was flat with time. But the stressed rock was systematically increasing the connectivity. And the interpretation was that the cracks which extended in the principal stress direction were opening up new connections and providing for a more conductive rock. But this was and Dave Lochner calls it the world's longest creep experiment. Ted wanted to run the longest creep experiment. As far as we know, no one has ever done this since. And we should find the data and get back on that one. But just an example of Ted getting into all kinds of different areas. Very versatile, very, very solid guy. So that's it.